Good morning, students. In my last lecture, I had discussed with you some of the NP complete problems like I had discussed with you CNF SAT and circuit SAT. And we had proved that these two problems, circuit SAT and CNF SAT, are your NP complete problems. Now in this lecture, I'm going to take three SAT problem. This is also a variation of SAT problem and we will prove that 3 SAT is also NP complete. So in the previous lecture, like I had taken this CNF SAT. Again, this is the variation of SAT problem that is called conjunctive normal form. Like you have been given a Boolean formula that is end of or clauses. Like you have been given, these are called clauses. You have been given this clause and this clause. And in this clause, all the variables are odd and here also these are odd. And all of these clauses are and we had proved that this Boolean formula is satisfiable, and in order to prove that this is satisfiable I had taken one circuit SAT problem and I had reduced that circuit SAT to CNF SAT. Like if you want to prove that CNF SAT is NP complete, first you need to prove this is a decision problem. Next, this should be in NP. Next, we need to prove that this is NP hard. Now you can prove that CNF SAT is NP hard by taking some another problem that is already proved to be NP hard. For that, we had taken circuit SAT and we had reduced this circuit SAT to CNF SAT in polynomial time. Now next I'm going to take this 3 SAT problem and we will prove that 3 SAT is also NP complete. Okay, first of all, what is this 3 SAT problem? Again, this is a satisfiability problem. That means we have been given a Boolean formula and but here we will restrict that Boolean formula to have only 3 literals in each clause. That means in each clause, like here in CNF SAT, in each clause you may have lesser than 3 variables or literals. But in 3 SAT, in each clause we can't have 1 or 2 literals, you need to have 3 literals. So that is the restriction. So this you can say is the restricted version of CNF SAT. So in 3 SAT problem, we restrict the Boolean function to have only 3 literals in each clause and check for satisfiability. It is the restricted version of CNF SAT. Now in order to prove that 3 SAT is NP complete, first thing is that we need to prove that 3 SAT is a decision problem. Now why this is a decision problem? Because again you have been given a Boolean formula and for different values of inputs we need to prove that whether the Boolean function, the output is 1 or 0. So this is a decision problem. Next is that we have to prove that this is in NP. Now, in order to prove that this is in NP, NP means we can write down a non-deterministic algorithm that can be solved in polynomial time. So again, actually this is a variation of SAT problem. You can use the same algorithm that we have used for SAT problem. And by using that algorithm, we can prove that this problem can be solved in polynomial time, but we need to use non-deterministic algorithm. So for non-deterministic algorithms, suppose this Boolean formula is given. For different values of these inputs like m and z, suppose if I'm taking them as 0, 0, 0, I need to check whether the output is 1 or 0. If it is 1, that means it is satisfiable. So we can write down algorithm that can be solved in polynomial time and it will check for whether the BFG is evaluates to 1 or not. So this we can say is an P problem. Now next thing is the third one, we need to prove that 3 SAT is a NP hard problem. Now in order to prove that this is NP hard, we need to take one problem like I'm taking here CNF SAT and I will reduce that CNF SAT to 3 SAT problem. If I'm able to reduce CNF SAT to 3 SAT in polynomial time, I can say that 3 SAT is also NP hard because we have already proved that CNF SAT is a NP hard problem. So in order to prove this thing, I'm taking one formula, Ci is equal to m plus n, that is in CNF format. This is not in 3 sat because in this clause you are not having 3 literals. They are only 2 literals. So I'm taking one CNF sat formula and I will reduce that to 3 sat in polynomial time. Now here, m plus n can be written as m plus n and 1 because you know that whenever any variable is and with 1, if you are taking the and of that variable with 1, output will be that particular variable. So if a and 1 is a, you can say m plus 1 and 1 is m plus n. Okay, so here instead of writing m plus n, I have written m plus 1 and 1. Now here it is written 1. Now I'm taking one variable, arbitrary, any variable z. Instead of 1, can I write down z plus z bar? Like if you are taking z as 0, what would be the output of this? It will be 0 plus 1. So you're getting 1. And if z is 1, it will be 1 plus 0. So output is again 1. So m plus n and z plus z bar will give you actually m plus n only. So first of all, instead of m plus 1, I had written m plus 1 and 1. Then instead of 1, I have written here z plus z bar because anyway the output of this is 1. Now this thing can be written as m plus n plus z and m plus n plus z bar, where z is any arbitrary variable. So this formula is in 3 sat because here you are having 2 clauses and in each clause you are having 3 literals. So I have reduced this CNF to this 3 sat in polynomial time. Now here I had taken one CNF sat in which you are having 2 literals. Now next I am taking a formula in which you are having only 1 literal. That is suppose Ci is equal to m. Now here instead of m I can write down m and n plus n bar. Then I will be getting m plus n and m plus n bar. Then again you can add that with z plus z bar. So you will be getting this formula m plus n plus z and m plus n bar plus z, m plus n plus z bar and m plus z bar plus n bar. So here I had taken this formula that was in CNF and I had reduced that to 3 sat because here each clause is having 3 literals. So I have reduced that to this 3 sat in polynomial time. Next is this one. I have taken one Boolean formula in which now you are not having 1 or 2 or 3 literals but you are having k number of literals. So here k means you may have now more than 3 literals, like you may have 4 literals in one class. But here in 3 sat we need to take a maximum of 3 literals in each clause. So here I have reduced, I am going to reduce this thing to this Boolean formula in which each clause is having 3 literals. So in this CNF format, formula can be written like this: m1 plus m2 plus n1, where n1 is any arbitrary variable, and then you take this variable m3, then write down n2 bar plus n3, then and you write down m4, then n4 bar plus n5, then you can say m5 plus it will be n5 bar plus n6, so on. If you're writing here nk, it will be nk minus 3, the complement of that, and mk minus 1. Like this way you can write down this formula. So you can reduce any formula that is in the CNF format, you can reduce that to 3 sat in polynomial time. Now this Boolean formula that is in 3 sat, it will be 1 if Ci this is 1. So it is noticeable that for BFGI is equal to B1. This is BFGI. I have written Boolean formula for each gate If this is 1, then the value of clause CI is also 1. Thus the original clause C. In C you can have many of these clauses like C1, C2, C3. So original clause C is 1 if and only if BFG is 1. The total Boolean formula that you have written, that is 1. So we have reduced Ci to BFGI in polynomial time. So you can see 3 sat is also NP complete problem. Okay. So again I'm repeating this thing. How can you say that 3 sat is NP complete? First thing is that we need to prove that 3 sat is a decision problem. Next, we need to prove that 3 sat is in NP. For that, you can take any non-deterministic algorithm that can be solved in polynomial time. Next one is that we need to prove that 3 sat is NP hard. Now, in order to prove that this is NP hard, I had taken one problem that is already proved as NP hard. Like in previous lecture, we had proved that CNF sat is NP hard. Now, if I can reduce this CNF sat to 3 sat in polynomial time, then 3 sat will also become NP hard. So for that, you need to take one Boolean formula that is in CNF sat and you have to reduce that to 3 sat in polynomial time. If we are able to do this thing, then you can say that 3 sat is also NP complete problem. Now, what's the meaning of this one? Meaning of this is that if 3 sat is can be solved in polynomial time, then CNF sat can also be solved in polynomial time. Or you can say that if BFGI is 1, that means if any formula that is written in 3 sat format, if the value of that is 1, then the formula that was in CNF sat that would also be 1. You take any value of m1, m2, m3, m4 and mk minus 1 and all these arbitrary variables. Suppose if the value of that is 1, then for those values of m1, m2 and m3, the CI would also be 1. So 3 sat is also NP complete problem. Okay, so till now we have proved all these things. That every problem in NP is polynomial time reducible to circuit sat. This we did with the help of Cook's theorem. Next, you can say that the circuit sat is reducible to CNF sat in polynomial time. And next is that CNF sat is reducible to 3 sat in polynomial time. So what's the meaning of this? That if 3 sat can be solved in polynomial time, then CNF sat can also be solved in polynomial time. Now if this CNF sat can be solved in polynomial time, then circuit sat can also be solved in polynomial time. And if this circuit sat can be solved in polynomial time, then every problem in NP can be solved in polynomial time. So actually, till now we don't have any solution for all these problems by using deterministic algorithm. But in future, if you are having any deterministic algorithm for 3 sat, that means if 3 sat can be solved in polynomial time using deterministic algorithm, then we can say this can also be solved. If this can be solved, then this can also be solved. And if this circuit set can be solved, then every problem in NP can be solved by deterministic algorithm. So all the problems will be solved by using non-deterministic algorithm in polynomial time. So all these problems are actually computationally related. Related means if one can be solved, then others can also be solved. So in next lecture now, I would be taking one clique problem and I will prove that clique problem is also NP complete. Now, in order to prove that clique problem is NP complete, I will have to reduce CNF SAT to clique problem. So we will reduce CNF SAT to clique problem because CNF SAT is already proved to be NP hard and NP complete. And if I am able to reduce this to clique in polynomial time, this will also become NP complete problem. So I would be taking this click problem in my next lecture.